Before Stephen Hawking, black holes were not mysterious in the way they are today. They were not paradoxes. They were not thermodynamic objects. They were, in many ways, boring. In classical general relativity, a black hole is defined by a very simple idea: a region of space-time from which nothing can escape. Once matter crosses the event horizon, all future paths point inward. No signal, no information, no light. This idea comes directly from Einstein's equations, first through the Schwarzschild solution, 1916, later generalized to rotating and charged black holes. Mathematically, black holes were described by just a few parameters: mass, charge, angular momentum. This led to what physicists later called the no-hair theorem. Black holes are completely described by a small set of numbers. Everything else, the shape of the star, the chemical composition, the complexity of collapse, was erased. Black holes were thought to be perfect absorbers and perfectly cold. Temperature in physics is not just a feeling, it is a precise concept tied to microscopic degrees of freedom. A hot object emits radiation, has internal motion, possesses entropy. But a classical black hole absorbs radiation, emits nothing, has no visible internal structure. So physicists concluded black holes must have zero temperature. If temperature is emission and emission is impossible, then temperature must vanish. This assumption seemed airtight. Before Hawking, physics lived in separate kingdoms: general relativity, gravity, space-time, black holes; quantum mechanics, particles, fields, uncertainty; thermodynamics, heat, entropy, irreversibility. Black holes belonged to gravity only. Quantum theory was considered irrelevant because the curvature scale of astrophysical black holes is large. Quantum effects were assumed negligible. Stephen Hawking himself initially shared this view. In the early 1970s, something unsettling appeared. Physicists like Jacob Bekenstein noticed that black holes obey laws that look suspiciously like thermodynamics. For example, the area of the event horizon never decreases. This resembled the second law of thermodynamics. Bekenstein proposed a radical idea: black holes might have entropy proportional to their horizon area. This was deeply controversial. Entropy was supposed to count microscopic states, but black holes had no visible microstates. Stephen Hawking initially rejected Bekenstein's idea. At this stage, Hawking believed black holes have area, but not entropy. They obey mechanical laws, not thermodynamic ones. This disagreement would soon lead to one of the most important calculations in modern physics. The question was deceptively simple: what happens to quantum fields near an event horizon? Not particles, not gravity itself, but quantum fields living in curved spacetime. This question did not require a full theory of quantum gravity. It only required taking quantum field theory seriously in a gravitational background. Hawking set out to prove Bekenstein wrong. Instead, he discovered something far more disturbing. To understand Hawking's equation, we must first unlearn a deeply ingrained idea. The vacuum is not the same for all observers. This single insight is the doorway to everything that follows. In quantum field theory, particles are not fundamental. Fields are. An electron is an excitation of the electron field. A photon is an excitation of the electromagnetic field. Even when there are no particles, the fields remain. This state, with no particles detected, is called the vacuum. But crucially, the vacuum is not nothing. It is the lowest energy configuration of a field. Here is a subtle but essential point. Particles are not absolute objects. They depend on how time is defined, how motion is measured, how space-time is sliced. Different observers can disagree on what counts as a particle. This was already known from the Unruh effect. An accelerating observer sees particles, an inertial observer sees vacuum. Hawking realized an event horizon creates a similar situation. An event horizon is not just a boundary in space, it is a boundary in causality. Outside the horizon, time flows normally. Inside the horizon, time and space switch roles. There is no single definition of time that works everywhere. And quantum fields require a definition of time to define particles. This mismatch is the heart of Hawking's calculation. Popular explanations talk about virtual particle pairs popping out of the vacuum. This imagery is misleading if taken literally. What actually happens, field modes near the horizon get split. One part escapes to infinity, the other falls behind the horizon. To a distant observer, this looks like real radiation. No violation of energy conservation occurs globally, but locally, something remarkable happens. When Hawking completed the calculation in 1974, the result was unavoidable. Black holes emit thermal radiation, not weakly, not approximately, but exactly like a blackbody. This radiation had a precise temperature, and that temperature depended only on the black hole's mass and fundamental constants. This was the equation that changed everything. This is the equation that forced physics to confront itself. The Hawking temperature is given by T equals h bar times c cubed over 8 times pi times g times m times kb. You do not need to calculate with it, but you must understand what it means. This single expression contains h bar, Planck's constant, quantum mechanics, c, speed of light, relativity, g, gravitational constant, gravity, kb, Boltzmann constant, thermodynamics. This had never happened before. One equation unified quantum theory, gravity, and heat. Not philosophically, not metaphorically, but mathematically. The equation says, smaller black holes are hotter, larger black holes are colder. Black holes can lose mass. Black holes can evaporate. This shattered 3 assumptions. Black holes are eternal. Black holes have zero temperature. Black holes are isolated systems. They are none of these. Stephen Hawking later admitted, "It was a complete surprise to me." He had been trying to prove black holes could not have entropy. Instead, he discovered they radiate. They obey thermodynamics. They must have entropy. He changed his position publicly, a rare act in theoretical physics. This equation works, but we do not fully understand why. It points to missing microstates, unknown quantum gravity structure, the information paradox. It is not the end of the story, it is the beginning of a deeper problem. Hawking's temperature equation did something unavoidable. If a system has temperature, radiation, then it must have entropy. This is not philosophy, this is thermodynamics. In physics, temperature is not fundamental, entropy is. Temperature is defined as 1 over T equals partial S over partial E. If Hawking radiation exists, then energy flows, heat is exchanged, entropy must be defined. There is no consistent alternative. So Hawking was forced to accept Bekenstein's idea, not as speculation, but as necessity. The entropy of a black hole is S equals kb over c cubed times a to the 4th over g h bar, where a is the area of the event horizon, not volume, not interior structure. This result is astonishing. Every known physical system stores entropy in volume, counts microstates in space, but black holes store entropy on a surface, encode information on a boundary. This was the first concrete hint of what would later become the holographic principle. At the time, Hawking did not know this implication yet, but the equation was already whispering it. This question has no complete answer. Entropy normally counts the
the number of microscopic configurations consistent with a macroscopic state. But black holes appear to erase microscopic detail. So what is entropy counting? Possibilities? Quantum states of space-time itself? Horizon degrees of freedom? Unknown quantum gravity microstates? All of these remain active research areas. The equation is solid, the interpretation is not. Before Hawking, gravity was geometric, space-time was smooth, thermodynamics was unrelated. After Hawking, gravity has temperature, space-time has entropy, geometry behaves like matter. Einstein's equations were no longer purely classical, they were thermodynamic in disguise. Hawking radiation created a problem so deep that it still defines theoretical physics today. This is the black hole information paradox. In physics, information is not data or memory. It means the full quantum state of a system. Quantum mechanics demands time evolution is unitary, information is never destroyed. This principle has never been violated in any confirmed experiment.
Consider this sequence. Matter with detailed quantum information falls in, black hole forms, black hole emits Hawking radiation, black hole evaporates completely. The radiation is thermal, carries no memory of what fell in, so when evaporation ends, the information appears gone. This violates quantum mechanics. Stephen Hawking made a bold claim: information is destroyed by black holes. He argued event horizons sever causal connections permanently. Quantum gravity may violate unitarity. This was heretical. Many physicists refused to accept it. If information can be destroyed, quantum mechanics is incomplete. Predictability breaks, the foundations of physics collapse. This is not about black holes alone. It is about whether physics is internally consistent. Physicists like Gerard 't Hooft, Leonard Susskind argued fiercely against Hawking. They insisted information must escape somehow, but how exactly? Hawking radiation seemed featureless. The paradox was real. After decades of debate, Stephen Hawking changed his position. This was not a minor correction. It was a fundamental shift. In 2004, Hawking announced information is not destroyed. Black holes do not erase quantum states completely. He conceded the argument publicly. This was one of the most respected reversals in modern science. Hawking's concession solved nothing technically. We still do not know how information escapes, how radiation becomes correlated, how spacetime encodes quantum data. The paradox survives. Only the conclusion changed. Crucially, Hawking radiation remains correct, black hole temperature remains correct, black hole entropy remains correct. The problem is not the equation, the problem is our understanding of reality. This equation suggests spacetime has microscopic structure, gravity is emergent, not fundamental, information is more basic than geometry. Black holes are not exotic objects, they're windows into the foundations of physics. Late in life, Hawking argued event horizons may not be absolute. Information may be subtly encoded. Classical spacetime may be an approximation. Even at the end, he was still questioning his own discoveries. References: S.W. Hawking, Breakdown of Predictability in Gravitational Collapse, L. Susskind, The Black Hole War. Once Hawking conceded that information is not destroyed, physics faced a new demand. If information escapes, when and how does it come out? This question was first addressed clearly by Don Page, a physicist working closely with Hawking. The Page curve is not a physical curve in space. It is a curve that tracks entanglement entropy over time. Specifically, entropy between the black hole and its radiation. At the beginning, radiation is purely thermal. Entanglement entropy increases. At the end, if information is preserved, entropy must return to zero. The Page curve shows an initial rise, a turning point, a gradual decline. This turning point is called the Page time. For decades, Hawking's calculation predicted no decline. Entropy kept increasing. Information never returned. The Page curve represented a theoretical requirement, not a derived result. It was a challenge. Find a theory of gravity that produces this curve.
If the page curve is correct, early radiation is thermal, late radiation must carry correlations. This means that Hawking radiation is not purely random. Subtle quantum correlations must exist. These correlations are invisible to semi-classical calculations. They require quantum gravity.
The Hawking equation is correct, but incomplete. It describes average radiation, thermal behavior. It does not describe fine-grained quantum correlations. So the paradox was not a contradiction. It was a signal of missing physics. The strange fact that black hole entropy scales with area refused to go away. Eventually, physicists accepted its implication. Proposed by Tufte and refined by Susskind, all information inside a region of space can be described by data on its boundary. This was not philosophy. It was forced by black hole thermodynamics. Recall the entropy formula, S proportional to A. This says degrees of freedom scale with surface, not with volume. Gravity violates our deepest intuitions. Hawking's equation predicted this decades earlier. In the late 1990s, Juan Malbecena discovered a theory of gravity in a volume is equivalent to a quantum field theory on its boundary. This duality preserves information, produces the page curve, and resolves the paradox mathematically. In this framework, black hole evaporation is unitary. Hawking's paradox dissolves, but only in special spacetimes. If holography is true, spacetime is not fundamental. Geometry emerges from quantum information. The interior of a black hole is encoded non-locally. Reality becomes relational. Hawking did not invent holography, but without Hawking radiation, black hole entropy, the information paradox, holography would never have been discovered. Even holography did not end the story. A new problem emerged. Physicists identified three assumptions. Information is preserved, physics near the horizon is smooth, quantum field theory works locally. Shockingly, all three cannot be true simultaneously. Something must give. One radical idea: the event horizon is not smooth. An infalling observer is destroyed instantly. This firewall breaks Einstein's equivalence principle. Hawking was deeply uncomfortable with this. If firewalls exist, spacetime is not smooth. General relativity fails at horizons. Reality is fundamentally discontinuous. The cost is enormous. Near the end of his life, Hawking proposed no absolute event horizons, only apparent horizons. Information eventually escapes. This avoids firewalls, but leaves questions unanswered. Hawking radiation is one of the most reliable results in theoretical physics, and yet there is something profoundly disturbing about it. There is no agreed-upon local physical process that produces it. This is not a weakness of explanation, it is a feature of the theory. In ordinary physics, radiation comes from atoms, from accelerating charges, from identifiable microscopic events. But Hawking radiation does not originate from inside the black hole, does not originate from outside either. It is not emitted by the horizon. The horizon has no material structure. The radiation emerges from the global structure of spacetime itself. This already tells us something radical. Gravity is not a force in the usual sense. It reshapes the vacuum. The Hawking calculation depends on comparing quantum field modes in the distant past with modes in the distant future. Between them lies a collapsing spacetime and an event horizon. There is no single time coordinate that smoothly connects these regions. This means particle creation is not localizable. It is not something that happens somewhere. It is something that happens to the definition of particles. Physics is built on local causality, but Hawking radiation depends on spacetime regions that never communicate, relies on correlations across horizons, appears acausal from a local viewpoint. This suggests local quantum field theory is insufficient in curved spacetime, not wrong, but incomplete.
A deeper problem lurks beneath Hawking's derivation. When Hawking traced outgoing radiation backward in time, he found low-energy radiation today originates from extremely high-frequency modes near the horizon, so high that their wavelength becomes smaller than the Planck length. Known physics ceases to apply. This is called the trans-Planckian problem.
At trans-Planckian scales, space-time may not exist, quantum gravity dominates, continuum assumptions fail, and yet the Hawking temperature is insensitive to these details. This is strange. It suggests a form of universality, like thermodynamics, independent of microscopic structure. Thermodynamic laws do not depend on atomic details, only on macroscopic constraints. Hawking radiation behaves the same way. This leads to a powerful idea. Einstein's equations may be equations of state, not fundamental laws, but emergent relations. In 1995, Ted Jacobson did something extraordinary. He derived Einstein's field equations from thermodynamics. Jacobson assumed entropy proportional to horizon area, Clausius relation, delta Q equals T ds. From this alone, he recovered G mu nu equals 8 pi G T mu nu. This means gravity emerges from thermodynamic balance. Einstein's equations become equilibrium conditions. Jacobson's argument depends on local Rindler horizons, en route temperature, horizon entropy, all of which trace back to Hawking's insight. If gravity is emergent, space-time is not fundamental, curvature is collective behavior, geometry is secondary. This undermines the classical picture entirely. A newer idea goes even further. In holographic theories, space-time geometry is determined by entanglement entropy. Distance emerges from quantum correlations. The famous result, entanglement builds spacetime. Remove entanglement, spacetime disconnects. Black holes saturate entropy bounds, maximize entanglement. They are not exotic accidents. They are extreme thermodynamic states of spacetime. From this view, radiation carries away entanglement. Geometry adjusts accordingly. Evaporation is geometric reconfiguration. The black hole shrinks because its entanglement budget decreases. This is not metaphor. It is mathematically encoded in holographic models. One final descent, still not an ending. Temperature requires a notion of time, a generator of evolution. But general relativity treats time as coordinate dependent, so where does Hawking temperature live? Black hole evaporation is irreversible, increases coarse-grained entropy, defines a direction. This suggests time's arrow is not cosmological only, it is gravitational. Perhaps time emerges from entanglement flow. Horizons define temporal direction. Dynamics emerges from information transfer. If so, Hawking's equation is not about black holes, it is about why change exists at all. Hawking radiation does not come from virtual particles. It comes from a mismatch between field mode decompositions. This mismatch is precise, mathematical, and unavoidable. To quantize a field, phi of x, we must choose a time coordinate t, a notion of positive frequency modes. We expand. Phi equals the sum over I of AI ui plus AI dagger ui star. Here, ui are positive frequency modes. AI dagger creates particles. But this decomposition depends on how time is defined. In gravitational collapse, there are two inequivalent time coordinates: past null infinity, before collapse, future null infinity, after horizon forms. Each defines its own vacuum. 0 in does not equal 0 out. This inequality is the entire story. The two mode bases are related by this. U omega out equals the sum over omega prime of alpha omega omega prime U omega prime in plus beta omega omega prime U omega prime in star. Particle production occurs if and only if beta omega omega prime does not equal 0. Hawking computed these coefficients exactly. He found the magnitude of beta omega omega prime squared is proportional to 1 over e to the omega over th minus 1. This is a Planck distribution, not approximately, not heuristically, exactly. This is why Hawking trusted the result. In letters and later interviews, Hawking admitted, "I did not expect the spectrum to be exactly thermal." Exact thermality meant no memory, no structure, pure entropy. The paradox was born inside the mathematics, not interpretation. Hawking had another way of seeing the same result, more geometric, more subtle. Hawking analytically continued time. T goes to I tau. This turns Lorentzian spacetime into Euclidean manifold. Near the horizon, the metric becomes ds squared equals approximately rho squared d tau squared plus d rho squared. This is polar coordinates. To avoid a conical singularity, tau equals tau plus beta, where beta equals 1 over th. Temperature emerges as a geometric regularity condition. No particles, no dynamics, just geometry. This derivation avoids trans-Planckian moons, avoids collapse dynamics, uses global geometry. Hawking trusted it deeply. It told him that temperature is not an accident of dynamics, it is built into spacetime itself. Now we hit the core of Hawking's original mistake, mathematically precise. The full quantum state. Capital Psi is an element of the Hilbert space, inside, tensor Hilbert space, outside. An external observer cannot access the interior, so they describe the system by rho outside equals trace inside psi, psi naught. This trace operation destroys information. Hawking concluded psi in goes to rho out. Pure states evolve into mixed states. This violates unitarity. Rho goes to u, rho, u dagger. But Hawking argued quantum gravity may not be unitary. This was not careless. It was mathematically consistent given his assumptions. Later developments showed that the trace is only effective. The full Hilbert space remains pure. Factorization fails in gravity. The mistake was not algebraic. It was assuming a tensor product decomposition of spacetime. Modern progress came from a method Hawking himself used earlier in a different context. Entropy is computed as S equals minus trace of rho log rho. It's hard to calculate directly. So one computes trace of rho n and analytically continues n to 1. This is the replica trick. In recent work, 2019 to 2021, replica geometries include new saddle points. Replica wormholes appear. These were not considered in Hawking's era. Including them produces the Page curve, preserves unitarity, keeps Hawking radiation intact. The equation survives. The space-time picture changes. This is as deep as current theory goes. The entropy of radiation is S of R equals min of ext of area of partial I over 4G plus S bulk of R union I. Here, I is an island inside the black hole. Information is counted where you least expect it. Information about radiation is encoded inside the black hole even after evaporation. Locality fails. Naive causality fails. But Hawking's equation remains exact. The deepest resolution of Hawking's paradox uses Hawking's own tools, extends Hawking's own methods, confirms Hawking radiation, but overturns Hawking's spacetime intuition. The breakthrough that finally softened the information paradox did not come from black holes directly. It came from a rethinking of entropy itself. Given a density matrix ρ, define the modular Hamiltonian K equals minus ln ρ. This is not a true Hamiltonian, but it generates modular flow. Ρ equals e to the minus k. In quantum field theory, k is highly non-local, except in very special cases. One such case is a Rindler wedge. For a Rindler horizon, k equals 2 pi times the integral of x times t00 times d to the d minus 1x. This is exact. It tells us entanglement entropy generates boosts. Horizon thermality is kinematic. Hawking radiation and Unruh radiation are the same phenomenon seen through different geometries. Hawking knew this, but its consequences were not yet visible. Relative entropy, S of rho given sigma equals trace of rho times len rho minus rho times len sigma. It is always positive, monotonic. When applied to vacuum-subtracted states near horizons, relative entropy positivity implies Einstein's equations. This is not metaphor. Gravity emerges as a constraint on entanglement structure. Hawking's original paradox assumed H total equals H inside times H outside. This assumption is false in gravity. In gauge theories, physical states must satisfy constraints. Hilbert spaces do not factorize cleanly. Gravity is a gauge theory of diffeomorphisms. There is no local gauge invariant operator that creates a particle at a point. Everything is relational. To define an operator O of x, one must attach a gravitational Wilson line extending to infinity. This dressing knows about the entire spacetime, couples inside and outside. So the idea of tracing over the interior is already suspect. Hawking assumed factorization because nothing else was available at the time. The information paradox is not a breakdown of unitarity. It is a breakdown of naive subsystem decomposition. The paradox dissolves when subsystems cease to exist cleanly. The entropy formula, S of R equals extremum of A over 4G plus S of bulk. This is neither classical nor quantum. It is semi-classical extremization. The extremum can jump discontinuously, appear or disappear. This is why the page curve turns. The island region I can lie deep behind the horizon, can be space-like separated from R, yet it contributes to entropy of radiation. This is not a bug. It is the price of unitarity. Hawking valued locality, causal structure, geometric clarity. Islands violate all three, softly but decisively. Yet they preserve his equation. They preserve his temperature. They preserve evaporation. The mathematics betrays his spacetime intuition. Hawking trusted Euclidean gravity more than almost anyone, the gravitational partition function. There is no time evolution, no causal ordering. Thermodynamics emerges before dynamics. Entropy arises from dominant saddle points, topological contributions. The horizon is not a place, is a boundary condition. This aligns with Hawking's deepest instincts. Euclidean gravity is not well defined non-perturbatively. It suffers from conformal instabilities. Yet, every successful calculation of black hole entropy uses it. Hawking accepted this tension quietly. Late in life, Hawking began to soften his commitment to classical spacetime. Hawking proposed, apparent horizons replace event horizons. Information is delayed, not destroyed. This avoids firewalls, permanent loss, but lacks mathematical precision. Hawking increasingly spoke of effective descriptions, practical unpredictability, weather forecasting for black holes. He was retreating from absolutes. The Hawking equation works too well to be fundamental. It behaves like an equation of state, a thermodynamic law. Hawking never said this explicitly, but everything he trusted points there. We go one layer deeper, still no ending. In thermodynamics, temperature does not explain atoms. Atoms explain temperature. But Hawking radiation may be reversed. Geometry explains thermodynamics. Thermodynamics explains geometry. There may be no deeper story. Black holes may not be objects.
They may be consistency checks on quantum gravity, filters that eliminate inconsistent theories. Hawking radiation is the test signal. It means some questions have no answers, only constraints. Physics becomes self-consistency, not mechanism.
To understand how information escapes a black hole without violating Hawking's equation, modern physics had to abandon one of its oldest assumptions, that local operators define reality. In ordinary quantum field theory, operators act at points. Locality is fundamental. In gravity, there are no gauge-invariant local observables. Every operator must be gravitationally dressed. This means you cannot ask what happens at a point without reference to infinity. Hawking's calculation already hinted at this. It never depended on local processes near the horizon. In holographic theories, bulk fields are reconstructed from boundary operators. Interior information is encoded non-locally. Mathematically, psi bulk of x equals integral k x y times psi boundary y times dy. This tells us something unsettling. The interior of a black hole is not independent of the exterior. Hawking's inside versus outside separation was never exact. Some reconstructions depend on the global quantum state. This means the same operator can mean different things. The horizon is not a fixed place. Reality depends on entanglement context. Hawking resisted this idea, but his equation quietly demands it. The page time marks when entanglement entropy stops increasing and information begins to return, but nothing dramatic happens locally. No signal, no explosion, no horizon drama. This is crucial. Information return is not a physical event, it is a global reorganization. This fits Hawking radiation perfectly. In quantum gravity, time evolution is better described by modular Hamiltonians, entanglement flow. The clock is not external, it is relational. Hawking radiation evolves because entanglement evolves, not because something ticks near the horizon. Hawking feared firewalls, violent horizons, breakdown of smooth spacetime, but information can return without drama, because nothing local changes, only correlations do. We are now in a position to say something precise. The Hawking temperature equation is not a particle emission formula, a quantum correction to gravity, or a dynamical decay law. It is a consistency condition between geometry, quantum fields, and entropy. Like the ideal gas law, like the second law of thermodynamics, it does not explain microstructure, it constrains it. That is why trans-Planckian details don't matter. Microscopic models vary. The result never changes. The equation survives because any theory violating it is inconsistent. Stephen Hawking did not discover a new effect, he discovered a boundary condition on reality. Any universe with quantum fields, horizons, causality must obey his equation. That is why it changed everything. It is tempting to mythologize Hawking, but his real legacy is subtler. When the equation contradicted his beliefs, he did not reject it, he followed it. Even when it destroyed eternal black holes, classical determinism, local realism. Hawking was wrong about information loss, but he was honest about it. Physics advanced because he allowed his own ideas to collapse under calculation. That is rare. Hawking suspected space-time was emergent, horizons were approximate, geometry was not fundamental. But he never forced these ideas, he left them as pressure points. Let us now slow down. Black holes were once thought to be endpoints, graveyards, perfect absorbers. Hawking's equation changed that. They are now understood as thermodynamic systems, information processors, constraints on reality. not objects of destruction, but mirrors held up to our theories. The equation did not answer our deepest questions. It revealed which questions were wrongly framed. It showed that locality is fragile, time may be emergent, geometry remembers entropy, and that physics at its deepest level may be less about mechanisms and more about consistency. Stephen Hawking once said, "My goal is simple. It is a complete understanding of the universe." Ironically, his greatest discovery taught us the opposite, that some equations do not explain the universe, they limit what the universe can be. And in that limit, we begin to see reality not as solid and absolute, but as something that holds together, barely, through entropy, information, and law. Final references. S. W. Hawking, Particle Creation by Black Holes, 1975. J. D. Bekenstein, Black Holes and Entropy, 1973. R. Wald, Quantum Field Theory in Curved Spacetime. D. Page, Information in Black Hole Radiation. A. Almiri et al., The Page Curve from Quantum Extremal Surfaces. T. Jacobson, Thermodynamics of Spacetime. L. Susskind, The Black Hole War. Final references. S. W. Hawking, Particle Creation by Black Holes, 1975. J. D. Bekenstein, Black Holes and Entropy, 1973. R. Wald, Quantum Field Theory in Curved Spacetime. D. Page, Information in Black Hole Radiation. A. Almiri et al., The Page Curve from Quantum Extremal Surfaces. T. Jacobson, Thermodynamics of Spacetime. L. Susskind, The Black Hole War.